My objective in this video is to try to explain conservation laws in terms of symmetry using little to no mathematics. So that's the goal. Okay, so let's begin. So I'm going to call this conservation laws and symmetry. Conservation laws and symmetry. So let's make an opening statement. So we can say that the argument xy is symmetric if xy equals yx. And this is a reflection symmetry. Reflection symmetry. Because clearly we have what looks like xy being reflected in a mirror to give yx. Okay, so imagine, what do we mean by symmetric? Well, you could have, a face. So just imagine a face. So if somebody has an eye here, try my best to draw an eye, and then an eye that's here. We talk about somebody has face symmetry. So that's the symmetry here. But if we had, let's say, for whatever reason, a bigger eye, a mirror, and maybe a smaller eye, then that would be no symmetry. So here symmetry just means same. No symmetry means different. Okay. So we've made an initial statement. Consider the following process. Consider the following process. So let's act on A, where A is just an object, with another object B. So let's say we act, and act is definitely deliberately vague, act on some object A with something that we will call B. And let's say on this occasion it gives the outcome 7. So the numerical value 7. So whatever A is, we did it on B, whatever B is, and we got the answer 7. Okay, so we've done that. Let's do it again. Then let's act on 7. So let's repeat the process on the outcome of the first process. Let's act on 7 with B again. And let's say, and I'm not saying you should predict that this would happen, but let's say ahead of time that you get the answer 7 again. So to give the answer 7. Then let's do it again, see what happens. Let's say you act on 7 again with B, whatever B is, and then you notice that you get the answer 7 again. Okay, so I've only shown 3 repeats here, but you could carry this on more than 3 times, so let's say an infinite number of times, or better yet, a finite large number of times. So let's repeat. Then what do we know about this process? Whenever I act on A with B, I get 7. And then if I repeat it, now A is 7, I repeat the acting with the B again, and I get the same outcome, 7. So what can we conclude about this process? Clearly, in this process, A equals 7, which is a conserved value. So which is conserved. Conserved here just means doesn't change. So let's clarify what we mean by conserved here. We mean not changing. Okay, because after all, we're trying to look at conservation laws and something called symmetry, which we started to introduce, but we're going to try and do it without practically any mathematics, which is definitely challenging. Okay. However, so there's definitely a but here. However, it is possible that A is conserved. Another alternate interpretation of the results. A seems to be conserved, yet A is not equal to 7. So this casts doubt on our clearly statement earlier. So it's not so clear anymore. So I want to try and qualify, again, without any to little mathematics, that it looks like, based on the data, A is equal to 7, and that seems to repeat, it doesn't change, so it's conserved. So it's not changing, but there's no reason to think that A is equal to 7. So that sounds weird. At least initially it should sound weird. Okay, so let's go on to, I'm going to insert a new page. Page down, let's see. Yeah, I guess I just want a new page. How can one do a new page here? Okay, I'm just gonna insert a new page. I guess it's gonna go backwards, but that's okay. Okay. So let's continue. If A is conserved, which we said in the previous page, then A equals 7, but if it's not necessarily 7, we can say it would have to be plus or minus C, where C is a constant. Okay. And the constant is allowed to have any value n. Okay. So again, why are we entertaining constant? Well, on the first page, so remember, because this way I'm doing it, the pages are going upwards, which is definitely vogue, if nothing else. It's possible that a is conserved, yet a is not equal to 0. Well, we just say plus or minus a constant, so we can scale it by a constant. Okay. Thus, if c is equal to 0, that's an allowed value of n. Then a is equal to 7, because a is equal to 7 plus 0. My dog's yapping in the background, which is amazing. But if, for example, c is equal to 1, then a is equal to 7 plus or minus 1, which could be 8 if it's plus, or 6 if it's minus. And obviously, if c is equal to any value n, then a is equal to 7 plus or minus n, which equals 7 plus n, or 7 minus n. Okay, so this is about as mathy as this video is going to get, so I'm stripping away all the math, and I'm going to try and explain this to a 5-year-old. Okay, or maybe a 5.5-year-old. Okay. Consider a visual example, if you please. Consider a visual example. Okay. So let's say, why a visual? Just to make it, picture speaks 1,000 words. So I might say 1,000 words with the picture anyway, but I could potentially not say anything and the picture would say everything. So let's consider some columns. Let's consider this column and then an adjacent column. And then let's say we have a column down here. Okay, and then let's say this small square on top of each column is the outcome of B acting on A, which is on number 7. Okay, and let's say we'll put some axes here. So let's say this is measuring height. So literally it's the height of a column. Okay, and 7 is the result of A acting on B acting on A. Okay, then the extra bit here, I'm going to call it n, where n is a value of the constant, so it's an allowed value of our constant. This is a different value, so let's call it n prime, where the prime just indicates it's a different numerical value. And this is different again, so let's call this n double prime. Again, just a different allowed numerical value. There's no reason why n has to be positive. So let's say if this is 0 and these are plus values, we could have minus values down here. So we could have, so let's say this is A, B, and C. We could have a value D, where we have our, because remember it's plus or minus this constant. So we could have n triple prime, which is just a different value again. Yet when we act on A with B, we still get the outcome 7. So we still return the outcome 7. Okay, so we've got 4 cases, A, B, C, and D. We always get the conserved outcome 7, yet we can have a variety of different constants, n. So let's draw a legend for this. So let's say that this is the act of B on A, as indicated earlier. Let's say that the shaded part is the constant. C with values n, and we know that n does not equal n prime, does not equal n double prime, does not equal n triple prime. It could, but there's no reason why it is. Okay, so that's a nice visual to see, to reconcile how we can have A equaling the act of B on A returning a constant, a conserved value rather, plus or minus a constant. So that's a visual example of how it could happen. Let's make a statement about that. Use that word clearly again. You should probably never say clearly. Clearly, the act of B on A apparently, from the data we have at least, always returns 7. That's the outcome. So we notice we have evidence, we have a conserved outcome to this experiment. But the outcomes can incorporate the outcomes can incorporate a difference. And that's the constant of value n. So conserved and constant used with different meanings, very, very tricky. That doesn't alter the conserved status, doesn't alter the conserved status. So as we can see, it's conserved, but with an allowable difference. Okay, which qualifies our assertion at the end of the first page that we have evidence that the act of B on A, so the act on A with B, so B is doing something to A, returns the number 7. But it can, even though it always returns 7, it can do so with plus or minus a constant that would still allow us to conclude that it returned the value 7. Okay. Okay, let's move on to the next page. Okay, I guess it's put me here. We'll move on to this page. Let's look at something I'm going to call reflection symmetry. Again, I'll try not to use any mathematics. Reflection symmetry. Reflection symmetry. Okay, let's make an opening statement. Okay. If, let's say we have X and Y, and then let's say we have a mirror here. So let's call it, that dashed line is a mirror. And what does a mirror do? It reflects, hence reflection. I'll just put singular for reasons that will become obvious in a second, not reflects, reflect. Well, if you reflect X and Y in a mirror, you should get Y and X. And I'm not going to bother drawing the Y backwards. You know, it's clear that whatever that object I've called Y is would be exactly the same in the other side of the mirror. So let's say we take X and Y, we reflect in a mirror. Then let's say we reflect the reflection in another mirror. So let's take another mirror and let's reflect again. Then we should get X and Y. And we notice that if we take the original after the second reflection, we get something that's exactly the same. Okay, we've returned exactly to where we were, and I'd have no idea, if you left the room and I did this, you'd have no idea that I did it because it's exactly the same. So that's a visual. So let's write something that's not mathy, I promise. You'd be fooled into thinking it's mathy, but I'll just use words. So with that visual, then we can say that this act, remember we were talking about the act of B on A, we'll let the act be a reflect act. Then the act of reflect on XY, so we reflect on the object XY, well that clearly gave us YX, right? That's what we had here. We reflect on XY, we get YX. And if we do it twice, so we do reflect and a second reflect, so it's not or, it's and, reflect and reflect on the object XY. So we take XY, reflect and reflect, well then you return XY again. Okay, which is exactly the statement we made that in the visual above. Okay, so we can make some conclusions here. If reflect gives you the reflection, but reflect and reflect essentially gives you the reflection of the reflection, you get the original again. We can make a concluding statement. Thus, reflect and reflect that act of reflect and reflect must equal 1, since only one acting on it, shouldn't say multiply, that sounds like math. Only one acting on XY can return XY. And that's exactly what we said reflect and reflect did. It returned the original. So the act must be numerically equal to 1. Okay, well, there's different ways you can get, well, there's potentially an infinite number of ways you can write the number 1. Let's pick one whose origins are in math, but we don't need to mention it because this is a math-free zone. Almost exclusively a math-free zone. That's the challenge. So I'm going to pick let reflect and reflect let that act of reflect and reflect, which is equal to 1. Well, anything to the power 0 is equal to 1, right? But I'm going to take the number e and have that to the power 0. So anything to the 0 is 1. I specifically want e to the 0 for reasons that we don't need to worry about here. Well, that means that whatever 0 is, it must be something minus itself. So let's say that that is e to the a minus a. Okay, so a minus a is 0, e to the a minus a is e to the 0, e to the 0 is 1, and that's exactly what reflect and reflect did. Okay, so we're doing good. Okay. Now, what could A be? We need to invent what A could be. So let's see how much room I've got left. Okay, I'll try and fit this bit on the next page, on this page. So we need to invent whatever A is. We need to invent whatever we're going to call A, and we're going to do it using our imagination. So let's call A, I for imaginary. Imaginary or imagination. And if we do that, then we therefore are saying that e to the 0 is therefore e to the I minus I, where A is just now relabeled I, which equals e to the I e to the minus I. So we've got one of them with a positive because it's a positive I, one of them therefore has to be a negative because when they sum together they give e to the 0. So we've just learned something about I. Let's see what we've just learned about I. So we've just learned that I has to be the square root of -1. Why does it have to be the square root of -1? Since 1 is e to the I, e to the minus I, which is what we just said above here from our argument about reflect and reflect. And if I is square root of -1, that would mean it's e to the square root of -1, and then e to the minus square root of -1. Well, I've got to add these, right? If I take the product of exponents, I take the sum of the exponents. So I've got two roots, which would cancel each other out. Or even a cleaner way to look at it, you've got something minus itself. So when I take it as e to the something minus itself, I just get 0. Done and done. Which is exactly what we wanted. Okay. Okay. So incorporating everything we've just seen into everything we saw earlier, So incorporating our constant c, remember our constant c, which can have values of n, which we'll generalize as delta. So this is the Greek letter delta, which means change. Okay. Then we have, if we take this idea here, just to give you a clue where I'm looking at, then we've got e to the I delta squared, because I've got two of them, so it's squared. That's equal to 1. So it's same argument, I've just added delta into the mix, which was our constant. Or, you square root that, we've got e to the I delta can be plus or minus 1. So either e to the I delta squared is 1, or e to the I delta, when we take the square root, is plus or minus 1. Because if it's plus 1, you square plus 1, you get 1. You square minus 1, you also get 1. Alright, I'm going to hit insert new page and wonder where this new page is going to show. So apparently when you hit insert page, it just inserts anywhere. Good to know. Okay, let's incorporate the results. So let's incorporating this result, which result? This result, e to the I delta is plus or minus 1. That's the result I want to incorporate. Okay, let's look at our xy again. So we've got xy. We've got our mirror, which there's no reason why it can't be straight. No reason at all. Our mirror to give us yx. This is our active reflect. Let's do it again. Another mirror. Let's say that that is a second active reflect. And if it did, it would give us xy again. Let's do it again. We have another mirror. That would give us yx again with a third active reflect. And we could do this ad nauseum, on and on, before and after. Just constant reflect, reflect, reflect. Okay, so let's incorporate that old image, but with our new result. So let's see what that would give us. Well, if we go from the, let's say we start, or at least we inspect, we don't know if this is the initial position, but let's inspect from here to here, one active reflect. So one active reflect, we have e to the I delta is minus 1. Minus 1 because we got the mirror image of the original, so we essentially multiplied it by negative 1. If we do a second reflect act, and go all the way here, in fact, when I say all the way here, I mean here. I mean all the way there, don't I? We go all the way here, then that would be e to the I delta is plus 1. Because we didn't get the invert image, we got the original image again. So we just multiplied the whole thing by plus 1. Let's go to the last one, at least in this diagram. Let's go all the way to Yish Kebab. Let's go all the way here. Then this would be e to the I delta is negative 1 again, because we've got the invert image again. So you see from this short collection that we have, as promised, the two outcomes, plus and minus 1, following n tuples of the active B on A. So we've got plus or minus 1 as our only two outcomes. Okay, so let's write that in a sentence-ish. So thus, we've just seen that the act reflect on the object xy can give you plus 1 it can give you plus 1, well actually I really should say not the act of reflect. I should say, well, let me erase this. I'm glad I've just caught this now. Okay. An odd number of reflect acts on xy can give you negative 1 on xy, which gives you yx. Okay, so we can see that in the diagram above. Odd number of reflect acts, let's say 1 and 3. So here we've got 1 tuple, a number 2 tuple, a number 3 tuple. So the odd ones are 1 and 3. So they give us an e to the I delta of negative 1, which gives us that invert image, as shown here. And then we've got an even number of reflect acts on xy. Well, that will give you plus 1 on xy, which just gives you xy. The only even one I have in the diagram above, but you could extrapolate to 4 and 6, etc. So an even number of reflect acts here, I've got 2. It gives you plus 1, which when it hits xy, it just returns xy again. So the mirror image of the mirror image. Okay, all good. So let's conclude this page by saying that we can generalize. We can generalize this expression to any act where when I say act, when I spell act properly, where act is e to the I delta. Okay, so we're going to generalize that to any act, because so far we've just been saying the word act. We kind of implied with the first example that here act was a reflect act, but it doesn't have to be, as we'll see now when I insert this page randomly, who knows where. Okay, obviously it went there. Okay, and this will actually be the last page of this video. So in general, let the act equal e to the I delta, as we said in the last page. Okay. If, on this occasion, act is rotation. That's an act. So let's say act is rotation. Then delta, which is our constant, remember, conventionally, and if I label this in a certain way, it'll allow me to tie it in with other videos I have on my channel. And I can sew the tiny gaps between these videos together. So I'm going to let delta be m phi. M phi, where m is just a number. So m is a number, a real number, but that's not important because we're not looking at math. Just a number. And phi is an angle, and here it would make sense that it's the angle of rotation. Okay. So let's make a note of rotation. That's going to be important. Here, this is the Greek letter phi. Okay, so phi is the angle of rotation. Thus, the act rotation is e to the I m phi. Okay, so we've gone from the general act as e to the I delta, where delta is a constant. Now act is specifically rotation. Delta is specifically m phi. So rotation, the act rotation is e to the I m phi. Crucially here, m is angular momentum. Now, remember, all along we've been talking about symmetry and conserved quantities. So we know we have argued symmetry. So we have used symmetry arguments and practically no math to show that angular momentum is a conserved quantity. Okay, and that's no small feat. So angular momentum is a conserved quantity. What if the act is displacement? So if the act is displacement, what's the difference between rotation and displacement? You could say, if you wanted to generalize it further, rotation is just a change in an absolute location. No, you wouldn't. You would say rotation on a fixed point is just a precession around the fixed point. So it's a relative change, and displacement would be an absolute change. You've absolutely changed where you are. Anyway, so the act, let's say the act in this case is displacement. Then let's try and write it the same way I've written the one above. Then delta is Ka, where K is a number, and A is a distance along some axis, X or Y or Z, it doesn't really matter here. Okay, so here we're talking about displacement, linear displacement. Okay, linear displacement, thus we could say that displacement is specifically e to the I Ka, and by doing so here, K is linear momentum. Alright, so we've got displacement, we've got linear momentum, and we have just shown we've used symmetry arguments and little to no math, so it can be done, to show that linear momentum is conserved. Okay, last one we're going to do. It's not the last one we could do, but it's the last one we will do. And we've got plenty of room. If the act is a temporal change, a temporal change. I can't figure out one word that summarizes temporal change. A temporal displacement, but it's still two words. Temporal change, then delta is minus omega t, and the minus here for omega, the only way to explain it would be to talk mathy, and the whole point of this video is to try and eliminate as much math as possible. So just accept that it's a convention that omega has a negative sign in front of it. where omega is a number, and t is time. Okay, so we've got temporal change, essentially a change in time. This is the Greek letter omega. It's like a W with a curly bit at the end, omega. Okay. Okay, thus, so I'm even being symmetric the way I'm writing this, which is just too much. Thus, temporal change, the act of temporal change, is e to the minus I omega t. And here, as written, that number we called omega is interpreted as energy. So we've got linear momentum, angular momentum, and energy. So to conclude this page, the final page, and the final page of the video, we have just used symmetry arguments and no math, almost no math, to show that energy is conserved. Okay, so I have other videos where we do use math to show the same thing, but this is showing in a fundamental way that energy is conserved. And that is the end of this video. Hope you liked it.